at the end of last week what is the concept of flow control, or what's the need. We want to make sure that the sender doesn't send too fast such that it overflows the receiver. The sender sends data. The receiver has a certain or a limited amount of memory to store the data that it receives. It stores it in memory, processes the data and sends it up to the next layer, if we look at the data link layer perspective. If the sender transmits the data too fast such that it fills up the memory, if the receiver has a slow processor, it takes a lot of time to process each frame. It's processing a frame, but at the same time it's receiving many other frames. Because it has a limited amount of memory, at some point it may fill up the memory, and the next frame that arrives, if the memory is full, is going to be what we say is dropped. That is, the receiver cannot store that next frame. It's dropped, that is, it's discarded, which means effectively that frame that was sent has been lost. It doesn't get to the destination. So somehow we're going to have to fix that later. We don't want to have that situation occur. If we lose data, it's bad because, and we'll see after flow control, we normally need some error control in that we would have to retransmit that data. Sending again is wasteful of our resources. We'd like to send everything just once. So we don't want this situation to occur where we fill up the memory and then another frame arrives and we lose it or discard it. We don't want that to happen because it leads to a throughput reduction, poor performance for our network or our link. So what we do is that the receiver controls the flow of data that it receives by telling the sender, slow down if you're sending too fast, or if it's not sending fast enough, speed up. So it controls the speed at which the sender sends the data. Of course, the link data rate limits the maximum speed at which it can send, but what the receiver can do is tell the sender, stop sending. Stop sending because I'm still processing the data, and once it's got some space to store more frames, you can say start sending again, so that over time it's not sending too fast to overflow the receiver. That's the concept of flow control. We want to avoid overloading the receiver. We need to go through the different protocols for the receiver to tell the sender to stop sending, how it can tell it that, and also how they perform. We'll go through two main concepts. Before we go through the protocols, let's give some terminology which we'll use in flow control and other protocols. That's what we've said. So before we look at flow control, let's look at how we may illustrate any protocol. Because when I describe how a protocol works, we'll often use, instead of just text, some diagram to illustrate what's happening. Here's, going back to our first 1 or 2 lectures, here's our 5-layer protocol stack. Computer A is sending data to computer B. We can look at it within an individual computer from a layer perspective where that data is generated, let's say by the user, and it flows through all the layers. They do their processing on that data, create some packet, add some headers, send it to the next layer, and so on. Eventually the physical layer sends some signals across the link which represent the data that's being sent. The physical layer at the receiver processes those signals, gets the bits back, and processes, sends up through the layers until the user at computer B receives the data. That's a simple view of the flow of data through the stacks. At each layer, because this is a computer doing some processing, performing some operations, there may be a processing delay. So there's some processing at the application layer. It takes time. In many cases, we assume because computers are quite fast, the processing delay is quite small. Nanoseconds, microseconds. Sometimes we ignore it because it's so small. But in practice, there's always some processing delay in the individual layers. Shifting data between memory inside the computer, for example, takes time. There's queuing delay in some cases. When we have many packets to send or many frames to send, some may have to wait for the others to be transmitted. So they must wait in a queue or wait in memory. Of course, across the link, we know it takes time for the physical layer to send signals out. That's our transmission delay. And it takes time for those signals to propagate across the link, propagation delay. So there's some concepts we know from before. I've captured part of that here on the board, but just from the network layer down. Let's focus on the data link layer and introduce some terminology. The network layer sends some data to the data link layer. We'll often call that a datagram. Okay? It's just the name of that block of data that's sent from the network layer to the data link layer, say a datagram. It's a sequence of bits, okay, representing some data and maybe some headers. When I draw this datagram, rather than drawing the sequence of bits like I have here on the board, this example, we won't draw the exact values of the bits. Often we'll just draw it as a rectangle representing some sequence of bits, some data. Okay? So you'll see that we'll draw the data that comes to the data link layer as, I'll draw it as some rectangle here. The data link layer takes this input data. So from the data link layer's perspective, this is the data coming in. So sometimes it's referred as just the data. Sometimes we'll refer to it as a payload. The thing that we need to carry by the data link layer protocol. That's the input to the data link layer. The data link layer does some processing and normally adds some header information to support the protocol, source and destination addresses, and other things. And sometimes even adds something to the end, a trailer, for example, for error detection, a parity check, a CRC check. So the way we'll draw that is simply, this is the input from the higher layer. The data link layer creates a frame, which is sent to the physical layer. And I'll draw the frame as, here's what came into the data link layer, and we'll often add a header, HDR for header, and sometimes we'll add a trailer. That is some extra information to the end. This is from the data link layer's perspective, this is the payload. This is the information, the data that we need to carry. The header and the trailer contain some extra information to support the protocol operation. Some overhead information, but we need them normally for the protocol to work well. So this is just illustrating how I will draw these frames. Sometimes I will not draw a trailer, simply draw a header and the payload or the data. Sometimes I'll write here the data. So we'll call this a frame, okay? And then the physical layer takes this and treats it really as a long sequence of bits, converts those bits into signals, and transmits the signals across the link. At the receiving computer, it receives the signals, converts back to bits, sends it to the data link layer as a frame. The data link layer stores that in memory, or we sometimes call it in a buffer, but stores it in memory, and processes and sends this part up to the network layer. And in fact, the higher layers follow a similar approach where we encapsulate the data into a packet by adding a header and a trailer. And that happens at each of the layers, or potentially can happen at each of the layers. The layers may do it differently. They may have different structure of header and trailer. So we now talk about frames, sending frames, as opposed to sending bits and signals. Okay? That's the main point here. And when we come to flow control, the problem is that the receiver has a limited amount of memory to store the incoming frames. If the memory is full, and a new frame arrives, that new frame is going to be dropped or lost, and that's a bad thing. We want to avoid that. So that's some terminology. We'll refer to frames as being sent. Sometimes you may more generally be called packets, frames or packets. So looking specifically at the data link layer, the steps are the data arrives from the network layer. Maybe it's queued. Maybe it has to wait for some other data to be sent. It's processed. We transmit the frame by really sending it to the physical layer. The physical layer transmits the signals. We can think that the signals representing that frame propagate across the link, are received. The signals are received and the frame is received by eventually the data link layer here. It's processed, potentially queued, and then delivered up to the network layer. And then the network layer goes to work, which may be similar. How do we illustrate these steps? How do we clearly show a diagram that illustrates the steps and the timing of those steps? That's important. We'll often use these what's called message sequence diagrams or time sequence diagrams. They show those steps, or at least some of those steps, related to time. And all I'm trying to do now is illustrate some examples that show the format of these diagrams, and then we'll see some real ones later. So those steps that we just went through, we have two computers, on the left A, on the right B. We went through 8 steps here, and over time. So one way to show that is here we have this vertical line representing what's happening at computer A, and another line representing what's happening at computer B. And time increases as we go down in this diagram. So at some point in time, the data arrives from the network layer. There may be some processing and queuing. That takes time. In this example, I haven't drawn the processing and queuing. We'll see why shortly. Or it's simply to make the diagram simpler, because usually they're quite small. Okay? At some point, we start transmitting the frame. So we have a frame to send. We start transmitting it. It takes time to transmit. And this rectangle here is illustrating the transmission of the frame. So we start transmitting at this time, and depending upon the size of the frame and the data rate, we finish transmitting at this time. So we'll use this rectangle to indicate the transmission of the frame. Of course, our signals representing the frame must also propagate across the link. So there's some transmission delay, the rectangle, and there's also some propagation delay. If we think of the first bit that is sent, the signal representing that propagates across the link, and it takes some time. If we start transmitting here, the propagation delay from here to here, that is this period, means that at this point in time, B receives that signal. Okay? So if the first bit was transmitted by A at this time, sometime later, remember time is increasing as we go down, sometime later the first bit would be received by B, and then the second bit and the third bit and so on, and eventually the last bit representing that frame would be received. And at that point in time, B has received the entire frame and can start processing that. We normally transmit one frame and receive, after we receive the entire frame, then we deal with that frame, we process it. We don't start processing the frame, or at least we'll assume we don't start processing the frame until we receive the entire frame. Okay? Once we've received that entire frame, we can send it up. Once we've received it and processed, we can send it up to the data link layer. That's send it up to the network layer. From the data link layer's perspective, the data has been delivered from A to B from that point. So we're going to use these diagrams, and you'll see them throughout the rest of the course, to illustrate how a protocol may work. or as an example of how the frames or packets are delivered between two computers. They importantly, we will use them to show the transmission time and the propagation time, propagation delay. It helps in calculating the total time it takes to deliver the data and then calculating throughput and so on. So simplified, we can say, okay, this represents the transmission time and this is the propagation time. So although here I've drawn a line to represent the first bit, I could draw a line for the second bit and all the bits. To keep the diagram simple, normally we'll just draw, like this. A rectangle to represent the transmission time of that frame and one line at the end to indicate the propagation delay. Let's see how that works, or see there's some examples of that by going through some flow control protocols. So now, flow control. Receiver needs to tell the sender to slow down. When it's receiving too fast or is filling up its memory, tell the sender to slow down so that it's got more space available in the memory. How does that work? Well, the simplest protocol we have available to implement flow control is called stop and wait, the stop and wait flow control protocol. It's quite simple in that what happens is that the sender sends one data frame and then it stops, waits for the receiver to tell it that it can send the next data frame. And the way that the receiver tells the sender that it can send the next data frame is to send a special frame called an acknowledgement or an ACK frame. So we send a data frame from A to B. When B has processed that data frame, it sends back an acknowledgement saying, thank you, you can now send the next data frame. It sends the next data frame, waits for an ACK. When it receives an ACK, it sends the next data frame, and so on. Send a data frame, stop, and wait for an acknowledgement to come back. So we have two types of frames now. So we can often, a frame in general may contain a header, a trailer, some data. In fact, it doesn't have to contain a trailer. It doesn't have to contain data. Normally there'll be a header. We'll distinguish a data frame is the frame that contains the information we want to send from A to B. It has data in it. An ACK frame is a special frame, and in our case has no data. It's just a header. It's just a special message saying, I acknowledge that I've received the data, you can send the next piece of data. So we talk about an ACK or an acknowledgement frame. So this is a protocol, and remember back to our first lecture when we spoke about how do you introduce someone, and when you greet someone, we went through this protocol of how do you greet someone, how do you Y to someone, and we wrote down some rules for that protocol. Well, here's an example of some simple rules for the stop and wait protocol. The source transmits a data frame when it has some data available to send. My computer wants to send some data to B. It transmits a data frame. Then the source waits for an ACK frame. It stops and waits for an ACK frame, and it must receive an ACK frame before it can send the next data frame. If the source has a lot of data to send from A to B, it sends the first piece in a frame, then waits for an ACK, and it cannot send the next piece of data, the next data frame, until it receives the ACK for the previous one. That's the source. When the destination receives a data frame, once it processes that data frame and it's ready for more data, it will send back an acknowledgement. So the destination receives the data, does some processing, it's got some space in its buffer to receive more, so it then sends back an ACK. saying I'm ready for another one. And if the destination is busy, it's processing a frame, its memory is full, it cannot receive any more, then the way to stop any more arriving is simply not send an ACK. Delay the sending of an ACK. So the destination can control the flow of data to it, the way that it's, or the timing of sending ACKs. If you send an acknowledgement, it means you want more data. If you do not want any more data at the moment, don't send an acknowledgement. So we'll get this sequence of, in the best case, send some data, receive an ACK. Send some data, receive an ACK. Data, ACK, and so on. Here's an example in our time sequence diagram. We've got data to be sent from A to B. Note, I show with this arrow here, data 1 arrives. What that means is data 1 arrives from the higher layer, the network layer. Maybe someone has pressed a button on the computer A to send some data at some point in time. So eventually it arrives at the data link layer ready to send at this point in time. So at the start, computer A is allowed to send a data frame. When it's starting the protocol, we transmit a data frame. It takes time to transmit that data frame, and that's shown by the rectangle here. So we say data frame 1 is transmitted from A to B. It propagates across the link. Eventually, the entire data frame 1 is received by computer B. At this time, it's received. Computer B may process that. So it takes some time to process that data frame. And once it's processed and there's some space available in the buffer for another data frame, computer B sends back this special ACK frame, which is really just a header. There's no data in this acknowledgement frame. Sends back an ACK frame, and that's coming back to computer A. Computer A transmitted data frame 1, and then at this time it's doing nothing. It's doing nothing, it's got nothing to send. Then at this time, computer A, the user, generates some more data to send. There's more data to send, okay? But according to the stop and wait flow control protocol, it's not allowed to send this data because it's waiting for the ACK for the previous data. So even though it has data ready to send, it's not allowed to send it. It has to wait for the ACK. When the ACK comes back, everything's successful, it can now send data 2. Transmit data 2, computer B receives data frame 2, sends back an ACK, the data is delivered. There was no processing shown here in this example. ACK comes back, again from computer A, transmitted data frame 2, received the ACK. It's allowed to send more data. At this point in time, it has no more data to send. So it does nothing until it has data to send. So at this point in time, the third piece of data arrives. It has some to send, transmit, and the diagram stops there, but it can keep going, propagate, ACK, and keep going forever. Okay? So when computer A has data to send, it can transmit that data if it's received an ACK for the previous data frame. When computer B receives a data frame, once it has space in its buffer ready to receive another one, it transmits an ACK. And they keep doing this until they stop operating. So the diagram keeps going. So the protocol is very simple. Okay, stop and wait, one of the simplest protocols we'll see. What we care about is not just how it operates, but how it performs. Now we've got some data to send. So our original data was to send. We put it inside a frame, we add a header, some trailer. we transmit that data, and then there's some time spent not sending data. We see here, from A's perspective, sending some data, not sending. Sending some data, not sending. This time spent not sending is, we can think, is inefficient. We've got a link from A to B, we've paid for that link, but we're not using it for some period of time. So the time spent not sending leads to inefficiencies.
Explain the wait for buffer space.
Wait for buffer space. So just in this example, what's happened is B received the data. Okay, let's say the buffer, I'll not draw it here, it's too hard, but let's say B has a buffer or memory, and we draw, here's the buffer, the amount of space available to store a frame. It receives data frame 1 and stores it in the buffer. So fills up the buffer. Okay? Because the buffer is full, it cannot receive any more frames. So at this point in time, imagine the buffer is full. The memory is full. So if it did receive more data frames, it would not be able to store them in the buffer and therefore would lose that data. That's what we don't want. So it waits until some space becomes available here. Now, how does space become available? It becomes available if we process whatever is in the buffer and send it up to the next layer. So it's successfully delivered to the next layer. Then it's their problem to deal with. Okay? So when we've processed that data, we remove it from the buffer. Or we remove it from that portion of memory. And if we remove that data from the buffer, then we now have the space available, and then we can send back an ACK saying, okay, I have space in my buffer for another frame. Send an ACK, and that allows A to send the next frame.
So the buffer space is filled with data from frame 1?
Yes. Yeah, the buffer, I think, is storing the data from the frames that are received.
Any particular reason for not having the second frame?
No. Just in this example, in the second case, imagine it goes in the buffer, but in this case, it's very fast to process. It goes in and immediately comes out. So I've just drawn it as that it immediately goes in and out. In reality, it takes some time, but the processing time to receive it sometimes will be very small. So often we'll see these diagrams where it's immediate. But in practice, it can take some time. It's just illustrating the two different cases. It depends upon the processing delay at the receiver, which we know can vary and it's hard to predict. Of course, it depends upon the buffer space available. Because if my buffer was twice as large and received the first frame, the frame takes up half of the buffer, we've still got some space available to receive the next frame, so we could send back an ACK. Okay? So if we still have some space available, some free space in the buffer, we can immediately send back an acknowledgement, for example. So we send an ACK when we have enough space available to receive the next data frame. It depends upon the size of the buffer, the size of the frames. What we'd like to know is if we use this protocol, how efficient we are in using our link. I pay my 10,000 baht a month for a 1 megabit per second link. If I pay some money per month to use that link, I would like to be using it as efficiently as possible. I'd like to be sending data across that link as often as possible. But we see here, with this protocol, we're not always sending data. We're spending some time not sending data. In fact, we're spending some time sending header as well, not the real data. So we can measure how efficient we use the link or what the throughput is if we use this protocol. Here's your chance to draw a diagram like this, and along with that, calculate the throughput or efficiency of using a link. So the example, and you need to do this in the next, try it over the next 5 or 10 minutes, I'll come around and help. We have a source computer A. It has 3 messages to send, each of 1,000 bytes. So our frame is going to contain 1,000 bytes of data, and the data frame also is going to have a 20-byte header. So if we draw the data frame, there'll be a 20-byte header and 1,000 bytes of data. And we're going to have 3 frames, okay? No trailer, to keep it simple. When a destination receives a data frame, it takes 1 microsecond to process that. So think of this time here as 1 microsecond. We receive a data frame, 1 microsecond later, we've processed, we can send back an ACK. An ACK is just a header. So it's just 20 bytes in length, say this part. We have a link which is 2 kilometers, and the speed of transmission of that link is 200 million meters per second. It's not the speed of light. It's not 300 million. Just to keep the calculation simple, it's 200 million. And our data rate of our link is 1 megabit per second. What is the throughput? If we use the stop and wait flow control protocol, what's the maximum throughput we can achieve? So what I want you to do is start drawing this diagram for our scenario and calculate how long does it take to transmit? How long does it take to propagate? And start, and the suggestion is, assume this is time 0. If the transmission time is 10 microseconds, as an example, if this is time 0, this would be time 10. And if the propagation was 1 microsecond, if this was time 10, this would be time 11. And if this was 1 microsecond, this would be time 12. So if you keep track of the different time points, you'll see if we start at time 0, at what time do we end transmitting the data?
Basically, before data frame 3.
Why is there space here? Because A has no data to send. Here, A had some data to send. It transmitted a frame. It has some more data to send. It's not allowed to transmit that frame because it has to wait for an ACK. Once it receives the ACK, it can immediately send this data. Receives an ACK, it's got nothing to send. If you've got nothing to send, you do not transmit. Then it has something to send, and then it transmits. So if it has nothing to send, it will not send the data frame. In this example that you need to draw, it's got 3 frames to send at the start. Try and draw the diagram and calculate the timing. In particular, the transmission delay and propagation delay. Maybe it's easy to, at the start to calculate, in this example, what is the transmission delay of our data frame, what is the transmission delay of our header, of our ACK frame, and what is the link propagation delay. Calculate those. And this is stuff that you all were successful in the midterm for calculating, transmission and propagation delay. Then start drawing the time sequence diagram. you're going to need the transmission and propagation time, so calculate them and start drawing this time sequence diagram for stop and wait flow control. Calculate the transmission time of the data, transmission delay. Piece of paper, pencil, pen. Here's a piece of paper.
Destination have to process the frame. So, I mean, there is no queuing delay.
In this question, there's some processing delay at the destination, but there's no queuing delay. Ignore queuing. There's no processing at the source, or if there is, it's very, very small that we can ignore it. So to keep things simple, we just say that there's a small processing delay of 1 microsecond at the destination when it receives a frame. What about these values? What's the transmission delay for the data frame? What's the value? I've calculated it before. What's the transmission delay for the data frame? 8,160 microseconds. We have 1,020 bytes in total, or 8,160 bits. We're transmitting at a rate of 1 million bits per second. So 8,160 bits, 1 million bits per second is a transmission delay of 8,160 microseconds. It helps if you use the same units and prefixes throughout the question. And in this question, it turns out microseconds is a good one to use. As opposed to, I could write it as, which is the same as 0.008160 seconds. For me, at least, it's easier to add up whole numbers than decimals. Okay? So rather than using seconds, I'm going to use microseconds. So in the other values that we calculate, let's keep everything in microseconds. So sometimes I'll omit the units, assume it's microseconds if it's a time. Transmission delay of our ACK frame. The data frame was 1,000 bytes of data plus 20 bytes of header, 1,020 bytes or 8,160 bits. ACK frame is just 20 bytes of header or 160 bits. Transmission delay, 160 bits, 1 million bits per second. How many microseconds? You don't even need a calculator. $160 microseconds. Note when you divide by 1 mega, 1 megabit per second, if you just simply, instead of divide by 1 million, but divide by 1, you'll get the units in micro. Mega is 10 to the power of 6, the inverse is 10 to the minus 6, or micro. So 160 bits at 1 million bits per second is 160 microseconds. I've kept the values easy. Propagation delay. Quick, someone, propagation delay. How many microseconds? 10. 2,000 meters divided by 200 million meters per second gives 10 microseconds. Processing, we know from the question at the receiver, is 1 microsecond. That's given. Now, draw your diagram, and so the stop and wait, data, ACK, and so on, and start at time 0. So assume that the first data frame is sent at time 0, t equals 0. And if we start transmitting at time 0, if this is the data frame, data 1, if we start transmitting at time 0, the transmission time is 8,160 microseconds, then this time here would be 8160. That is, from here to here takes 8,160 microseconds. If you label these times on here, it's useful in calculating the total time. It's a very easy way to graphically see the total time. Data, draw the ACK, work out the time when those other frames are transmitted. Find the total time to deliver the 3 frames and get the final ACK.
Why don't we have propagation delay for both data and Analysing?
Why don't we have propagation delay for both data and ACK? We do, but they are the same. Propagation delay, our link is 2 kilometres in one direction and 2 kilometres in the other direction. It's the same length, okay? Therefore the same propagation delay. Send in one direction, propagation will be 10 microseconds. Send back, it will be 10 microseconds. The links in both directions are the same length and therefore same propagation delay, which is very common. Most time your link, or the distance to send the signal, is the same in both directions. Total time?
Yes.
Where's your picture?
About 20 milliseconds. 875.
Draw the diagram. If you draw this time sequence diagram, you'll see the total time. It will be very easy to calculate. That's the idea here, to see how the protocol works and the timing. Draw this diagram like you have on the previous slide.
Process for propagation like this. This one is
Yes, the processing delay, in our case, or in our question, the processing delay is once B receives the data frame, it takes some 1 microsecond to process, and then it will send back the ACK. Propagation delay is the time it takes to propagate the signal from A to B, which is really this time, propagation delay. Your diagram doesn't have to be to scale. Mine will not be to scale, but you can at least keep track of the time. Processing. The processing delay is used to determine how long it takes before the ACK comes back. In this example, B receives a data frame, processes, then sends an ACK. So the time between when we receive and send the ACK is the processing delay.
This is the end of the process.
I think most people, so you see the according to stop and wait, send the data, propagates, there's a little bit of processing at the destination, then it transmits the ACK, that propagates back. At the start, A had 3 data frames to send. It's allowed to send the first one, and it cannot send the second one until the ACK comes back. So when the ACK comes back, it can immediately send the second data frame. And it's the same procedure. They just keep following the same steps. Some processing, transmit an ACK back. And then you'll continue on and you'll do the third one. To calculate the throughput, which is what we're after in this question, we're going to need some information about how long this takes. Transmit, starting at time 0, takes 8,160 plus, although the entire frame is propagating, we'd think that the entire frame is received after the last bit arrives at B. If we start transmitting the last bit here, and it takes 10 microseconds to propagate, if we start transmitting at 8160 plus 10 microseconds to propagate, the 10 microseconds here, we'd receive that last bit at 8170. And if we receive the last bit, it means we've received the entire frame. Process plus 1, 8171. Transmit the ACK, takes 160. So we've finished transmitting the ACK at, what is it, 8331. Add the 160 here. The last bit of the ACK is transmitted at time 8331. It takes 10 to propagate, so it arrives at 8341. From that first frame's perspective, if we started at time 0, we'd receive the ACK at time 8341 from computer A, and then it can immediately send data frame 2. And it's in fact the same steps. We just repeat this again. And the third one we repeat again. So by drawing this diagram and calculating the time for each step, it's very easy to quickly get the total time it takes.
Does the last one is a quotient, in execute quotient?
In this case, yes, calculate the time it takes to get the last ACK there. So data ACK, data ACK, data ACK. And then tell me the time at which the last ACK is received. You don't have to draw, I'm not going to draw the last one because I've got no space. You can, but you may see there's a pattern there. If you recognise the pattern, you don't have to draw it. Second data frame's the same size, will take the same amount of time. It will plus 8160 brings us to 16501 here. Start at 8341 plus 8160 time 16501 here. Plus 10, plus 1, plus 160, plus another 10, and brings us to, if you add them up, you can check 16682. Who got that value? What did you have after the second?
Second, 25,000.
After the second, 16682. Anyone else? You can go through the steps. And then do it again for the third one. I'll draw it. Anyone get that value? Okay. 25023 sounds about the same. And I'll continue my diagram where? Over here. So after the second ACK arrives back, it's 16682. And then we start transmitting the third frame. Data, propagate, process, ACK, propagate. ACK 3. And you simply add on 8160 plus 10 plus 1 plus 160 plus 10. Sounds good. Just adding on those components and you should get to 25023. What's this time? The first data frame. Data, ACK, data, propagate, process, ACK, propagate. The time for the first data frame and to receive the ACK was 8341. For the second data frame, from here to here, what's the time? It's the same. Because in this example, it's the same data size, therefore same transmission, same propagation, all the values are the same procedure. And the last one is also 8341. And if we had not 3 frames, but 300 frames, it would just keep going. In the best case, every 8,341 microseconds, we transmit 1 frame and receive an ACK. And then if we have more data to send, you can keep going. Data, ACK, takes 8,341 microseconds. So this question's for 3 frames, but it can be easily extended to any number of frames. Any questions about how we get to there? How we get that final number of 25023 and that intermediate number of 8341? Because it's just repeated, I didn't go through all the steps for adding up those values. Now the question is, what is the throughput? Throughput is the rate at which we deliver the real data. The real data to the destination. Look at the destination B. We've drawn for 3 frames, but imagine it continues forever. Not 3 frames, 300, 3,000 frames. We just keep repeating this. From B's perspective, from A's perspective, it's transmitting 1 data frame every 8,341 microseconds. 1 data frame in the first 8341, another data frame in the next 8341, and so on. If we have data, we can say that A is transmitting 1 data frame every 8341 microseconds. And as a consequence, because the data is always received by B, we can say B is receiving 1 data frame every 8341 microseconds. Nothing is lost in this case. There are no errors. If A is sending 1 every 8341, B would be receiving 1 data frame every 8341 microseconds. let's write that down. B is receiving a data frame every 8341 microseconds. Even if we extended this to not just 3 frames, but 3 million frames, B would be receiving a frame every 8341 microseconds. And that tells us something about the throughput, because we know the throughput is the rate at which the real data is received. How much real data in one data frame? How much real data in one data frame? 1,000 bytes. The data frame contains a header, which is some overhead, plus the 1,000 bytes of real data. So one data frame contains 1,000 bytes of real data. Yeah, real data. And we're receiving 1,000 bytes of real data every 8341 microseconds. And if you divide, so the data size by the time here, you get what value? Someone had it before. This is 1,000 bytes or 8,000 bits. $8,000 convert to bits. Okay, that sounds right. Equals, if I convert this to bits, bits per second. I converted to from bytes to bits because I want to compare it to the data rate, which is in bits per second. You don't have to, but we'll compare it shortly. Throughput of 959,118 bits per second of real user data, ignoring the overhead. Our linked data rate was 1 megabit per second. That is 1 million bits per second. But our throughput is slightly less. The throughput is the rate at which we send the real data. And if we look at our diagram, if this is the time sending a data frame, some part is header. This is the real data. So visually we can say in this time, this blue part is the time spent sending real data. This is time spent sending header. This is time spent sending ACK. This is time spent waiting, propagating, processing, and so on. So time spent sending the real data, total time to deliver that, and the ratio gives us the efficiency of our protocol. And quite simply, the efficiency we have, if we have a data rate of 1 megabit per second, that's the maximum, 1 million bits per second, we can say the efficiency as a percent is 95.9118%. The data rate is 1 million bits per second. The rate at which we send the real data is 959,118 bits per second. The efficiency, therefore, is 95.9118%. We use 95.9% of the data rate to send the real data. The other, 4.1%, the other 4.1% of the time we spend not sending real data. We want this to be as high as possible. Similar, we want the throughput to be as high as possible. So efficiency is how efficiently do we use our data rate to send our real data, which is simply throughput divided by data rate, but expressed as a percentage. Any questions on how I calculated the throughput or the efficiency in this case? Because we'll use both, in fact. The efficiency is how good our protocol is. We have a particular link. We're using the stop and wait protocol. The efficiency measures how good that is in utilizing the link. We'll see there are alternative protocols. We'd like to use the most efficient protocol in sending our data. In this case, we measured an efficiency of 95.9%. What's the efficiency if I change the link distance from 2 kilometres to 200 kilometres? Same scenario, but the link is 100 times longer. If the link distance goes up, the propagation delay goes up. What's the efficiency? Does it go up or down? Simply change the link distance so the propagation delay goes from 10 microseconds up to 1,000 microseconds. Does the efficiency go up or down? Not the value, I don't want the value, you can calculate it, but does it go up or down? Some people have said down, some have said up. If the propagation delay goes up, try and visualize this diagram. This time would be larger. If this was 10, now it's 1,000, the total time to send our 1,000 bytes would be larger. It wouldn't be 8341, it would be larger. Okay? If the propagation delay goes up, this time will go up. If this time goes up, our throughput goes down. And if our throughput goes down, our efficiency goes down. Increasing the propagation delay decreases our efficiency. And what happens if we increase our data size? So 100 bytes, 1,000 bytes up to 10,000 bytes.
Efficiency would be more because there's a less ratio for the header towards the total data.
If we increase the data size from 1,000 up to say 10,000, this will increase from 1,000 to 10,000. This will increase, but correctly, the ratio of the data to the header will get smaller. There'll be less overhead from the header relative to the data, and our efficiency will go up. So there's different relationships between the data size, the propagation delay, and how it impacts upon the stop and wait flow control. Whenever you use stop and wait flow control, it's important to understand in your link what the efficiency will be, or what the throughput is. You can derive this equation and you can try different values to see that stop and wait generally, if we have a very high data rate, a large distance or small data frames, it's inefficient. That is, the efficiency will be low. Increase the link distance, efficiency goes down. Decrease the frame size, efficiency goes down. Increase the data rate, efficiency goes down. And therefore it gives an indicator of when it's useful for different types of links. Not so good for optical links, not so good for satellite links, because inefficient in those cases.